Thanks, first of all, for the invitation. So I've been asked to give an overview of what our current dark matter research is, mostly focusing on what we can do with a multi-wavelength approach. So let me start from the beginning, although most of you are aware of the fact that we have actually overwhelming evidence for the gravitational presence of dark matter at different scales, from rotation curves of galaxies up to the a very isotropic microwave background. We don't really know what dark matter is. We know that it represents the largest amount of matter in our universe, almost 80%. And to explain it is actually strikingly enough to add one extra ingredient which interacts only gravitationally with the rest of the matter content in the universe. So in the standard paradigm, dark matter is interpreted as particles beyond the known particles of our standard model for particle physics. However, the range of masses and the interaction cross-section that it can have with the standard model particle is quite huge. And what I would like to point out is that any time you want to engage in a strategy to try to identify the nature of dark matter particles, you always have some kind of theoretical prejudice about what you are looking for. So you always need some sort of signature of your model, and this determines what kind of data and the strategy you are engaging to look for it. On the other hand, we are living in a wealth of data from astronomy and astrophysics brought from space and from the ground at different wavelengths and with different messengers. So we have telescopes capturing the gamma ray radiation up to very high energies and arrays of interferometers giving us the image of the sky in radio wavelengths. On top of that, we can also probe cosmic ray particles and neutrinos with different kind of instruments. And we can actually exploit all this plethora of data to try to pinpoint what the nature of dark matter is. So the idea behind dark matter indirect detection is exactly this one, namely how we can exploit astroparticle experiment to get further insight onto the nature of dark matter particles. And in general, you have to rely on some kind of effects or signature that can distinguish the dark matter particle with respect to standard astrophysical backgrounds. And you want to do so by, on the one hand, optimizing analysis strategies, and on the other hand, actually looking into the data. And when data are not available, you actually ask for observation times to telescopes. So the guaranteed results that comes up from there are constraints on the dark matter particle model that we are interested in, as well as a better understanding of astrophysical background with a continuous feedback between those 2 points that allows you to proceed further onto your search. So there are 2 main model-independent tests. One is the standard indirect detection strategy based on the fact that dark matter particle can annihilate or decay in the halo of galaxies, leading to final stable fluxes, and this is what I will describe mostly in the following. But then you can also have purely gravitational probes where you exploit the fact that dark matter actually interacts gravitationally with standard model particles. And you can also exploit some of these channels to probe the dark matter particle nature. So the models that you can actually try to constrain are all those models that give an alteration of fluxes of charged particles or photons through either new production mechanisms or distortion effects. So you can do that with standard weakly interacting massive particles, for axion-like particles, and for sterile neutrinos, for example. And there will be talks addressing all these kind of candidates in this workshop. If I focus on the minimal weakly interacting massive particle scenario, then the interval of masses that we are interested in is around the GeV to TeV scale. And those are quite promising candidates because the freeze-out production mechanism naturally leads to a weak scale candidate that can explain the measured abundance of the cold dark matter in the universe as measured by the analysis of the cosmic microwave background temperature and isotropy. And it offers us a way to actually look for final stable products of the annihilation or decay process. So in this case, dark matter annihilation would lead to final stable particles of, for example, charged cosmic rays, neutrinos, or antiprotons and protons, as well as photons at different wavelengths. The energy distribution of the final state particle actually depends on the mass of the dark matter particle that you are considering, as well as the final channel that you are studying. And usually, to be model independent, indirect detection limits are set by assuming that the spectral energy distribution of the signal, so this the DNDE, is described by annihilation into 100 branching ratio into a final state. So this is just an example of what is the prompt photon spectrum that you expect from dark matter annihilation, expressed in terms of this dimensionless variable x, which is the energy of the photon divided by the mass of the dark matter particle, where you see at low energy there is a smooth and featureless emission that comes from the hadronization and decay of quark and boson final states. And then you can also have, in general, spectral features that are predicted at the high end of the energy spectrum. For example, gamma ray lines that arise in most models at one loop. And those kind of features are something that you can exploit in the optimization of your detection strategy. If you have dark matter annihilating into final leptons, then you also expect that those interact with the environment, giving some secondary emissions, producing photons. And this can be done for example, by a low energy photons being upscattered by the dark matter produced electrons or positrons up to gamma rays, when the low energy ambient photons come from, example, from cosmic microwave background light, starlight, or infrared light. You can have branch stratum or synchrotron radiation that will give unset a signal at radio frequencies. So the spectrum that you expect in the end from dark matter predictions is truly multi-wavelength. So this is the intensity of the flux, if you think, of the dark matter annihilation signal for annihilation into B quarks and 100 GeV mass as a function of frequency or energy, where you can see that the predicted dark matter spectrum has different peaks. This pi0 component is what is the prompt photon emission that for a candidate at the weak scale will fall into the gamma ray band. Then you have the inverse Compton peak at X-ray energies, and then the synchrotron peak at radio energies. So when you want to look for a signal for dark matter, you can actually combine all wavelengths in order to better get constraints on the parameter space. So as for what is the parameter space over for WIMP, so well, you can actually constrain it with different probes. For low WIMP masses, let's say below 10 GeV, is the cosmic microwave background that gives you the strongest constraints on WIMP particles, while at high energies are really observation of the gamma ray sky and of the charged cosmic rays that set the strongest constraints into the parameter space. And the parameter space is usually the annihilation cross-section as a function of the mass of the dark matter candidate, where you can see that if you recast correctly onto the plane of the total annihilation cross-section as a function of the mass, what is left consistently combining different experiences is an open window between, let's say, 10 GeV up to 100 TeV, where you can still have weakly interactive massive particles accounting for the data that you have used to set bounds. What is the signal that you are actually looking for? Well, this is an example of what you do expect for the flux of photons produced by dark matter annihilation that comes from this prompt emission I was describing before. This is the map of the full sky, where longitude runs on the x direction and latitude on the y direction, and the center is the galactic center. And the photons produced by dark matter annihilation are described by this master equation, where you see that there is a particle physics terms containing the information about the interaction cross-section, which makes directly the link with cosmology, and the mass of the candidate, as well as the spectral distribution of your signal. And on top of that, you also see that there is a kind of spatial distribution of the signal that you expect, which is very bright at the center, and then it fades out of the plane. So this is the shape of the signal is actually described by the spatial distribution of dark matter in the target that you are considering. And it is very sensitive, the flux of final photons is very sensitive to the distribution of dark matter in the targets, since it goes for annihilation as depends on the square of it, and they integrated along the line of sight. I just give an example of what we expect for the dark matter density as a function of distance from the galactic center from typical dark matter profiles that have been proposed in the literature are either motivated by simulations of galaxy formation or by observation of the galactic rotation curves. And in particular, there are two regimes. So with current observations, we cannot actually probe the profile of the Milky Way down to, let's say, 4 kiloparsecs at most, while in order to extrapolate at smaller scales, and this is what we need if we want to make searches of dark matter, for example, towards the center of the galaxy, then we have to rely on extrapolation from simulations. And the uncertainty that you have on the dark matter density is one of the largest theoretical uncertainties in your modeling that you have to account for when deriving constraints on dark matter models. On top of the smooth distribution of dark matter in halos, you also have that you expect small-scale structures to arise from the simulation of structure formation, and those are called dark matter subhalos or substructures. And some of them will trigger the formation of stars, and so they can be identified with optical counterparts and are usually classified as dwarf spheroidal galaxies. But most of them will actually be truly dark and will not have any stellar content. So the mass distribution of the subhalos in galaxies is actually one of the features that can allow you to distinguish, for example, cold dark matter candidates from warm dark matter ones. And you can, and there are actually gravitational searches that are aimed to disentangle what is the minimum mass of the subhalos in the universe in order to try to probe the nature of the dark matter particles. This is just an example of how you can use, for example, strong gravitational lensing to get an insight of what is the mass distribution of dark matter halos in the galaxy as a function of the subhalo mass distribution. And for the moment, those are actually constraining masses down to 10 to the 8, 10 to the 9 solar masses, so far away from the minimal halo mass predicted by different dark matter models. But in the future, this will greatly improve with observation of LSST and ALMA. And an example is in the next slide, where you can exploit gaps in stellar streams, and I think probably Mariangela Lisanti has talked about them yesterday, where you can exploit the perturbation induced by dark matter subhalos in stellar streams to set a bound on the minimal halo mass, so exploiting what is the stream brightness, and there are very good and promising prospects for what you can do with LSST. So then I will focus in the 5 minutes that remains on how we can actually probe the WIMP window with high energy photons. And there will be also dedicated talk about what we can do with very high energies for example, CTA later today. So the targets for dark matter are several, and how you choose the best target is actually a careful balance between what you expect from the signal, so which is proportional to this so-called J factor, which is the integral along the line of sight of the dark matter density square, with respect to your expectations for the background. And so you can have different targets, like pointing at the galactic center or at highest latitude, and all of these approaches have been undertaken in order to constrain particle physics model with photons at GeV energies, looking at the data of the LAT on aboard of the Fermi telescope satellite. So I will start with dwarf spheroidal galaxies, which are satellites of the Milky Way at about 100 kiloparsec distance from Earth. They are thought to be very clean targets for dark matter searches because they are thought to be dominated by dark matter with very little astrophysical emission. And on top of that, the advantage is that we have actually discovered many of them with optical surveys, and they can be considered as independent experiments that can be combined. And in the next slide, I explain how we can actually do that. So if you want to run an analysis of dwarf spheroidal galaxies, for example, with the LAT data, what you actually do is to build a joint likelihood which weights every dwarf with its J factor, and this allows you really to stack the data from different dwarfs and to improve the sensitivity to dark matter by means of this channel. So the status of limits from dwarfs, which will also be presented by Mattia Di Mauro later today, is that we can actually exclude a cross-section, thermal cross-section below 100 GeV masses. However, there are large uncertainties that affect the robustness of the determination of the content of dark matter in dwarfs, and this has been discussed in several papers, as well as the background uncertainties that you have in the determination of the astrophysical foreground and backgrounds at the dwarf position. And all these uncertainties actually can weaken the limits from dwarf by a factor of 2 to 3, putting them again in competition with other kind of targets. So in the future, we don't expect really the LAT to improve very much the limits. However, what we expect is the discovery of many new dwarfs. 100 of them are expected with the future LSST, and this will give us another set of constraints that we can make with gamma rays. And competitive bounds I want to mention, are also expected from future radio and X-ray telescopes, and there will be a dedicated talk of radio emission by Martin Follman on Thursday. As I said, the faint, let's say at the faint luminosity end of the subhalo mass function, there are the dark subhalos. So structures that will not emit any optical light, so will not have any counterpart in optical surveys, but will still be shining in gamma rays if they are actually dominated by dark matter, and dark matter is a standard WIMP. So the question that people have addressed is that if we have already detected those subhalos among currently unassociated gamma ray sources. And if you want to do so, what you have to do is actually to, on the one hand, have an estimate of the dark matter subhalo candidates that you expect from data, and on the other hand, have an estimate on the detectable number of gamma ray subhalos that you expect from your model. And to do so, you have first to have a model for the substructure distribution in the galaxy, and a model, or let's say an estimation of the detection threshold of the LAT. And if you do so, what you can see in the right plot here is the distribution of J factor as a function of the mass of the subhalo for the full dark matter subhalos in your simulations for a given prescription of the model. And only a few of them will be detectable, meaning that they will pass the detection threshold that you can see here on the left. So by comparing the number of expected candidate detectable sources with the number of dark matter subhalo candidates, what you can do is again to set a constraints on the cross-section as a function of the mass. And this will, of course, depend on the number of subhalo candidates that you have in your catalog, as well as on the subhalo modeling. So on the left, you can see how the constraints actually depend on the number of subhalo candidates that you have left in the catalog. And the limit, the reach, let's say, of your search is when you are able actually to exclude that all sources that are left unassociated in your catalog are actually dark matter subhalos. And this at the level of what we can do with dwarfs nowadays. And on the right instead, what you see is what is the effect of different modeling of the dark matter substructures in the galaxy, which also account for the baryonic effects of the tidal stripping in the Milky Way disk. But there will be a dedicated talk again about this type of search just right after me. As I was explaining, one of the possible targets is also to look at the diffuse extragalactic emission at high latitudes. And in this case, what you can exploit are basically the photons that you collect above and well above and below the galactic plane, where you basically get rid of all the bright emission from the galaxy. What you can do is actually to build several observations, several observables that are based on the counts of photons at high latitudes. So on the left, you see what is, for example, the all sky intensity averaged over the full high latitude sky that you can measure with the LAT, and those are the black points. And this receives a contribution from standard astrophysical sources, like here blazars, mesoline GN, star-forming galaxies, and plus spectrum radio quasars, but is also expected to receive contribution from all the dark matter in the universe, so extragalactic and galactic dark matter. So what you can do is to actually exploit this kind of observable to set constraints on the dark matter parameter space, and this is what has been done in the literature. But actually what it has been shown that you can improve on the limits that you can get and the constraining power that you have if you also exploit spatial and redshift features of your dark matter signal. And in the middle panel, you see, for example, what you do expect from the anisotropy measurements. So the Fermi-LAT has measured what are the small-scale fluctuations that you have in the photon counts at high latitudes, which are compatible with a Poissonian noise, so this straight line here where you see the Fermi-LAT band measurement. And if you compare with expectation again from standard astrophysical sources, where you only have a Poissonian noise or dark matter, you can see that you can exploit this kind of observable in order to try to detect first and then constrain dark matter. And in the end, finally, what you can also do is the cross-correlation with different type of tracers. And this is what people have proposed and what searches are currently about to try to cross-correlate the gamma-ray sky with several tracers like weak lensing or catalog of galaxies in the universe in order to highlight the presence of a dark matter signal, which will show up in a different way with respect to standard astrophysics, as you can see here by the difference in the different curves. So, as I said, the constraints from very high energy photons will be covered lately today. What I want to mention is that there is still an unexplored region in energy that could be very promising for dark matter, which is the sub-GeV sensitivity gap, where nowadays we only have observation by integral and COMTEL, but that we hope in the future will be covered by future instruments. And this can really push down the limits on dark matter at for masses of about 100 MeV. And there will be a talk about that on Thursday. I'm running out of time, so I will probably skip this part, but this was dedicated to the Galactic Center GVXS and to show you what this was about, but actually there will be a talk by Mattia, so I think I would just skip and go to the conclusion. which is there. So I hope I show you that astroparticle experiment can successfully test different dark matter models. I show you an example for WIMPs, but actually we can also do a lot for axion-like particles and primordial black holes. There are strong constraints that are set on the WIMP parameter space. However, it's very important to assess correctly the robustness in order to especially cross-checking signalings. There are some low-standing excesses. I hadn't time to talk about that, but you can really exploit the fully multi-messenger approach in order to refine your modeling and get further insights into the nature of those excesses. And finally, we are entering an era of real wealth of data with multiple experiments that are taking data now and will take data very soon, like LOFAR, SKA, Athena, and CTA at different wavelengths, and this will provide us access to yet uncharted portions of the parameter space for dark matter.